Of course, I myself am also very grateful to the organizers. Not so much because it's an unalloyed pleasure giving the talks, but still organizing isn't much of a pleasure at all, and they're doing it. And so I will not ask for another round of applause. That sort of gets in my nerves, but certainly I too appreciate all the work they had to do. So I'm afraid that this is the last lecture of the entire conference. Is that correct? Yes, well, I'm afraid the conference is ending with a whimper, not a bang. But conceivably, what I have to say in this lecture will be useful for some users. Lev, for instance, although I think he actually knows this stuff already, but someone who's doing his sort of work. So how does this all work out? Well, there's this long list, well, not long, there's this short list of maximal arithmetic subgroups gamma bar, and using all of the steps that we have described, we end up understanding those groups in a fairly concrete way. We have a fairly big list of elements for each of them. Those elements can be listed either in symbolic form, sort of algebra, or as floating point matrices. We have a presentation for the group, so we know no more than 3 elements which generate it, and we have relations. We have a list of elements which represent all conjugacy classes of torsion elements. That's useful if you're trying to figure out the torsion, not just in the group itself, but also in its finite index subgroups. Another thing that we worked out is for those torsion elements, we figured out the way in which they were acting on their fixed point, or if there was a fixed point fixed by a larger group, we figure out exactly what the action of that group was. That last information did not end up included in this. So of course, there's the usual Galois correspondence, to a smaller group, you get a larger quotient, and the ones that we were most interested in were subgroups of the right index so as to give us a fake plane, but they're also slightly larger groups which give us surfaces which are covered by the planes, fake planes, sometimes regularly, sometimes irregularly, and this document, which is available to anyone who wants it, lists all the fake planes, but also all of these surfaces covered by fake planes, and the calculations that were done here. Once we had everything else that I said, is basically straightforward and quick calculations. I did them with GAP, Donald did them with Magna, we cross-checked their results. I want to describe a few things about this so as to, just let people know what information is available immediately on the document, and also how the notation works. Has anyone figured out where the pointer is, the light pointer? No? Well, okay. Well, point at something. So let's see. Can I? All right, maybe I can use this guy. So for each fake plane, let us say, no, it's better to use this one, say. This is FPP. This entry in the table is a fake plane. We have a symbol that represents it, which has a certain number of items in a certain order, and I want to explain to you what those are. So, well, the first item here tells us what the two fields K and L are, right? In fact, if you look at the top line there, you see that just the, not exactly. The A equals 1 tells us that the two fields are supposed to be Q and Q with I being the square root of -1. If it was A equals 2, it would be the square root of -2. The P, on the other hand, this is telling us what division algebra we have. Now, you'll recall that the division algebra are always split over two different places of L, and those two different places always lie over a single place in K, and if K is Q, as it is in this case, a place means a prime, and so the P equals 5 means that for all of the ones with A equals 1, P equals 5, we look at the division algebra, which fails to split at the two 5-adic primes of L. Okay? It is important that it splits, and so in this case, for that particular field, the fact that it splits is the fact that there exists a square root of -1 in the 5 adics, which is true. Okay, so that's the first two items in this. What are our two fields, and where are the primes where we're splitting? Now, for each field, there's the story of what are the possible determinants of group elements. These always turn out to be, well, Donald explains this. These turn out to be S units in L, where S is the set of the two funny primes. So that 3 plus 4i over 5 is integral in L, except at the two 5-adic primes, and that is, and that it and its inverse, and the determinant, can be a power of that fundamental S unit, and in the table we've actually listed what it is in each case. Notice that it says modulo cubes. Well, that's because really we're looking at the projective group, so we can always multiply the determinant by any cube. So this is not giving us a map from our group to Z, it's giving us a map from our group to Z mod 3, depending on what sort of determinant we have. Okay, so now I come to the third element on the list. Now this is telling us about the parahorics. In fact, that set here, in this case it's the set with just 2 in it, is telling us at which places we want to use the type 2 parahoric, the funny one. Okay, so the other day Donald listed for a particular case 6 possibilities. Depending on what the first 2 elements is, there can be various possibilities for this set, but this means that at a 2-adic prime we're using a funny parahoric. Whereas if you look at the first one up there, that one there, you see it's the empty set. There we're not using funny parahorics anywhere. Okay, that's what the third element means. Okay, so now let's look at this one is as good as that, and it's closer. Okay, so this entry in the table is written FPP over 3. So that means this is not a fake projective plane. It's something which is covered in a threefold way by a fake projective plane, right? Again, with fairly, perfectly doable group theory calculations, we discover that the automorphism group of this is trivial. We've calculated the abelianization of the corresponding group, which is not exactly the fundamental group of the manifold, because this thing has singularities, but the group which is acting in the ball has an abelianization. It has been calculated. I'm not sure exactly what that means for any sort of geometry, but it's easy to calculate, so it's calculated. Rather more to the point, here's the fundamental group of this surface, singular surface, C4. To get the fundamental group of the singular surface, all you have to do is take the original group and mod out by all the torsion elements. So this is again, and we can also calculate the first homology, which is the same. Okay. In addition, this is quite detailed information, which possibly would be of interest to some user at some point, but it's not a fact which is mathematically fascinating. We can tell what things this is covered by. Okay, this particular surface is covered by two different fake planes, which are the ones with these, with these symbols. Okay. So for each item on the list, we explain, we give a list of both what it is covered by and what it covers. So, if this is useful. Now, obviously you need to be working on some specific problem in order for that information to be of interest to you, but if you need that information, it's certainly available. Some of these covers are regular, and some of them are not regular, and that's also listed. So that depends on whether, well, a regular cover is one that you get just by acting on the surface with a group of order 3 and taking the quotient. An irregular cover is something a little, that it's a not Galois cover. Okay, let's see. Now let's look at this symbol. This is so we have the same things. The field is determined by =1. The ramification of the division algebra is determined by p equals 5. The parahorics we want to use are given by this, but what's D3? Well, D3 is to explain in what way this subgroup, or the corresponding subgroup arises. Okay, we have here we have that surface which corresponds to a certain discrete group, and here we have something which covers that with index 3, so it corresponds to a index 3 subgroup, and this last thing is trying to say where does the index 3 subgroup arise? Okay, so this has to do with the question of whether these are congruent subgroups or not congruent subgroups. The question?
When you say that you computed the automorphism group,
yes.
The automorphism group of the surface,
Oh.
or just the automorphism coming from the ball?
That's a good question. Yeah, just the ones coming from the ball.
Also
So,
the smooth ones?
I think for the smooth ones we can be sure they all come from the ball, but you may know better than me. Yeah, okay, so this is a very good point. I mean, I seem to be imprecise. I'm definitely imprecise in the case of singular surfaces. It's exactly as Carlo says. The automorphism groups listed there, are the automorphisms which come from maps of the ball. If there are others, we don't see them. So this is, I mean, I'm not going to change the document, to each time it says automorphism group to say automorphism groups arising from ball automorphisms, but that's really what it is. Yeah. Excuse me? Yes, that's all. It's yes, that's exactly right. Again, with the generators and relations and everything else, is a very, very, very easy calculation for the programs to do. Nothing. Okay, so what does this D3 mean? Well, the sub 3 means that there's an index 3 condition. Actually, you can see that there's an index 3 condition between these two because one covers the other with index 3. So the sub 3 means it's a degree 3 condition. And the capital D means it's a degree 3 condition that arises from the determinant. See, the determinant was called D, large D of x. So in fact, this is the subgroup that you get if you only allow elements of determinant 1. Okay? And that gives you a degree 3 subgroup, and that was what was needed. Okay. Now, let's see. Okay. Now, here we have a different sort of thing in the third place. Recall that the third place is telling me which parahorics we're using, and to make this easy to remember, if you can remember it, I will draw a picture. So remember that when we look at the two-adic version of this group, when we tensor with Q mod 2, we get a certain sort of group which is acting on this sort of tree, known as the building for that locally compact group. And the two parahorics which give you maximal arithmetic subgroups correspond to either you're fixing a vertex of the one type or you're fixing a vertex of the other type. Two possibilities. Now, one of those would correspond to the case where we have empty set in third position. That would be when we fix a vertex of type 1. And the second one, when we have 2 in the set, which was called T1, corresponds to the case where we're fixing a vertex of type 2. So I don't know which is which. Completely arbitrary, but say that's type 1 and that's type 2. Well, that's good, but what does 2I stand for? That stands for the subgroup which is fixing both of them. Now that, of course, is not maximal. It's the intersection of the other two. Okay? But that subgroup has a name. That's called an Iwahori subgroup. The parahoric subgroups is a little play on words between parabolic and Iwahori. And so my I here is I for Iwahori. Now, what index does this Iwahori subgroup have in the two parahorics? The index is 3, obviously, because if we fix this point, then there would be 3 possibilities for where this goes, and we're only allowing 1, and likewise here. Okay? So we take the intersection of the two parahorics, and we get an Iwahori, which is at index 3 in each of them. Now, when we make this further this further intersection, the effect also on the arithmetic subgroup is to reduce it by size by a factor of 3. This is part of the of the mystery of arithmetic groups. So that means that this one here, where I use 2I instead of either 2 or, that is to say, where I fix an edge rather than fixing one of the two types of vertices, gives me a group which is 3 times smaller than the others, which means for this particular case that it's just the right size to be a finite projective plane by itself. Now, it ought to, that finite projective plane ought to cover either of the other two, and you see that it does, okay? You get a bigger group by deciding to fix just one of the others. So both of these two, if you check in the table, those are not themselves finite projective planes. They're finite, they're coverings, they're covers. They are covered by finite projective planes with index 3, and so this is working out exactly as you'd expect it to be. But anyway, this is what that notation 2I means like. Now, in the listing of classes in Gopal's papers, 2I is treated as a separate class distinct from the other two classes. Okay? This is just choice of conventions, but if you happen to be reading his paper, it's useful to understand that that is the way it is looked at. Okay. And this, in fact, finished everything with A equals 1, P equals 5, and then we go to A equals 2, P equals 3. So now the field is with the square root of -2, and the division algebra is ramified at the 3-adic places, and so forth and so on. I'm not going to read this to you line by line. That would be very boring. Just to give you an idea of what's available and how much we know. Basically the same stuff. Also here, when we talk about our subgroups, so far I've told you about 2 sorts of subgroups of index 3. One had to do with the determinant, and then there was the other which says that instead of just fixing this vertex, we will also fix that. Okay? So there are various ways in which how do I make it go down? Page down? Yeah, okay. So let me look at that 4th element. I want to find something other than D3, because there are indeed others. Okay, here's a good one. 2 with 7. The sub 7 means that this is an index 7 condition. The prime, the prime here, 2, says that it is an index 7 condition that is put on by looking at the two-adic place. It's basically a congruence condition modulo 2. Let's see if I can work that out a bit. Since p equals 2 here, we, in fact, at the two-adic place, we are looking inside a division algebra. But I believe that if you look at that division algebra modulo 2, it is no longer a division algebra, it is just, okay. First of all, we work at the p-adic place. So this means that we take our original division algebra and we tensor it with Q2. And this turns out, this gives us a division algebra D2. Then this can be reduced as a ring modulo 2, but when you do that, it's no longer a division algebra. It becomes just the matrices over Z mod 2. Okay, so that's a group of GL3. GL3 of Z mod 2, that's the group of 168 elements, right? And what I wrote here is false? Well, you can't very well get a division algebra because there isn't one.
You get something with uniform and radical.
No, you should take multiplicative group of the division algebra.
Yeah, well, of course. Well, all right. I have every reason to think that he's right and I'm wrong, but perhaps when we look at the multiplicative group, it does work out like this. In any case, okay, do you know what it comes as? I mean, it must be something that has a subgroup of index 7. It can't be just a thing, because there is in fact a congruence condition modulo 2 that picks out a subgroup of index 7. However, this is a detail which, you know, either one of us could work out with enough time. I just don't want to waste everyone else's time.
You a torus inside GL2.
Of GL3 of Z mod 2.
Yeah.
Yeah, well, I think that's what it is. But in any case, apart from these details, which I seem to have wrong, it's a degree 7 condition that is given by a congruence condition at the prime 2. That's the meaning of the notation. Okay. So here's another one. You see here it's actually a subgroup of order 21, and I put down 2 different things in this 4th slot. You use the determinant condition and that condition. Okay? So there can be more than one condition. But here's one. X. X is the unknown. You see it, it's known for this sort of group that you get lots of, in fact, this was discussed in the paper. Gosh, I'm blocking in his name. The young man yesterday who gave the talk about profinite completions, it is known for the, Stover, yes, that you have some finite index subgroups that come from congruence conditions, but also some that don't. And X stands for something that does not come from any congruence condition. Now, you might ask how I know that. Well, since I am very far from being an expert on these questions, it's, you know, there's maybe 1% possibility that I don't have it right, but essentially it's like this. To get the congruence condition, you do this sort of operation. First of all, you tensor with the two adics, and then you reduce, or not necessarily the two adics, it could be the p adics, and then you reduce modulo p, and looking at whatever you get over p, you put on a congruence condition. Well, you don't have to put it there at level 1. Maybe instead of, Basically, this map has to do with the map from, let's call it something else. Let's say the prime was 7. Okay, so to get that congruence condition I just described, you're basically using this map. You're reducing everything modulo 7. This is not required. You can get congruence conditions that are deeper. You can, okay? However, the extra congruence conditions that you would get from this sort of map would always have degree 7, okay? From this sort, you can get congruence conditions of various sorts, but for this one, no. And since this x7 condition is mysterious, it's really only at the prime 7 that one has to check that the condition that one's using is not this sort of condition. At the other primes, one can work out what the smallest index congruence condition can give you, and this grows with the prime. So, you know, one actually has to check that it's not this for the primes 2, 3, 5, 7. Probably that was enough. Beyond that, the least restrictive congruence condition that might possibly exist is, you know, has size bigger than index 7. It's because the maximal subgroups of the corresponding reductions are, you know, well, one knows what they are, and they're not that big, right? Their indexes are large. So since you can rule out all possibilities for how this thing could come from a congruence condition, it's a non-congruence condition. But I didn't actually write NC7 because I'm slightly worried that I don't understand these things well. I just call it X, mysterious. Okay, so that's what X stands for, a mysterious condition, you know, which is reducing the group by a factor of 7. You will observe that this is covering the thing without that condition by index 7, which of course it has to do because it's an index 7 condition. Okay, now I believe that's all I have to say about this for the next little while. The automorphism group is listed in one of the standard notations. I think this is the Atlas notation, but anyway, it's a standard notation. So this is a non-commutative automorphism group. Its first homology is C2 to the 4th, and Guillaume has abandoned my talk. Well, he's probably wise to do so since he's already read this paper, but I believe that this is the one that he was looking at, right? He wanted this automorphism group and that first homology, C2 to the 4th. Does anyone else remember that? And so as it happens, this is the only one on the list that has that, so this is the one he was talking about. All right. I believe I've explained everything that's needed here until we get to the example C2. Okay. Now, in the other cases, I just wrote an A, like A equals 7, and that corresponds to K is just Q, and L is Q adjoining the root of minus 7. But in the cases where the even K was of degree 2 over Q, instead of trying to list the numbers, we just used the notation that was on the list in Gopal and Saiki's paper, right? So in this case, K is the square root of 5, and to get L, you have to join the square root of minus 3. So that's totally real. This is totally complex. There's actually a difference for the determinant here, which is not based on the fact that it's, you know, that the space field is a little larger. It's based on the fact that we have the square root of minus 3. When you have the square root of minus 3, you have a cube root of 1. And this means that that you've got an extra S unit, namely the cube root of, not cube root of minus 1, cube root of 1. You have a cube root of 1. That's also an S unit. You know, the units of a field contain the whatever roots of unity happen to be included. And so if we've got that, that's also a possible determinant. So this means that our determinant will be actually given by two pieces. One piece which comes from a root of unity, and this other piece which comes from the S unit. Okay? Right. So that's a little difference. Whoops. We see how this is relevant when we start looking at subgroups that are picked out by conditions. You see, there's something picked out by a condition on, I believe that's the S unit part of the determinant, and here's something picked out by the cube root of unity part of the thing. Each of these is a condition of order 3. And this one here, on the other hand, we're picking out by both of them at once. So that actually gives us an order 9 subgroup. Okay? And here I have another mysterious condition, which I believe to be non-congruence. And here's yet another thing. I mean, basically our determinant group is Z3 cross Z3. So there's more than one, there are many ways to put on an order 3 condition. You can look at little d or at big D or at their product. That's fine. So that's what that means. I believe the reason I've wrote x prime here and x there is because it's not the same mysterious condition, so I wanted to make that clear. See, here we're looking at d squared d. So as a matter of fact, in these examples, you tend to get a lot of index 3 subgroups because someone will tell me how many index 3 subgroups there are in Z3 cross Z3. Yes? Not that many. 4? 4, yeah, okay. Well, again, I have no interest in showing you this table line by line. I just want to show you what sort of thing is in it. I guess for a certain sort of person, the most interesting thing about the table are really these non-congruence subgroups, although they're so mysterious that even in having the extremely concrete examples that we do, I doubt that they're going to be too useful in helping people understand non-congruent subgroups, but at least there's some examples. Here we've got a non-congruence, what appears to be a non-congruence condition that picks out a subgroup of index 9. All right, now, is there anything else that I need to say? I don't think so. Oh, no, yes, I remember there's another detail that comes up here. This is that, well, for one thing, this is that unusual case where L is not a Galois extension of Q. It is, of course, a Galois extension of K, being a order 2 extension, but not of Q. And it turns out that in this case, when you look at the primes at which we are going to use the strange, the less normal paraphoric, it turns out that in K, there are 2 different 17-adic primes. That's because there are 2 different square roots of 2 modulo 17. And it turns out that they behave different, that the behavior of the one is not the same as the behavior of the other when you pass up to L. This is possible because overall it's not a Galois extension. So when we say at the prime 17, we use the strange paraphoric, one has to understand that that is one of the 2 primes 17. It's not at both, and it has to be just the right one. It's a little detailed. Donald actually explained that previously, but surely it is one of the more detailed details. Okay. I believe I have now said everything that I want to say. See, now here's another one where we seem to have put on a condition at one of the 2 3-adic primes. Now, perhaps I'm mistaken in something I said earlier. Perhaps I didn't. Okay, in this case, the extension is Galois, and nonetheless, I'm putting on the condition at just one of the primes. I guess what this amounts to is I can put it on, if it's Galois, then all the three-adic primes are in the same orbit. So I can put the condition on it, the one or the other, and it amounts to the same thing. Whereas in the previous case, where it was not Galois, I had to be very careful to choose exactly the right 17-adic thing in order to make things work out. But also here, it's not really the rational place 3 that counts, but one of its two extensions in K. And that's the end of the file. Okay, so I bet that after this long conference, no one's going to be too angry because I didn't prepare a full hour's worth of talk. If anyone wants a copy of this thing, I will be happy to, to give it to you from my pen drive. If anyone wants to take a look at some particular detail, there are only 2 or 3 people in the room who might want to look at it. I mean, here I am as a consultant to help you use it, but I don't. Now this is interesting. I don't understand this. For some reason, which I actually do not understand, 3 plus and 3 minus are different here. Yes, no. I think I know what it amounts to. To switch back and forth between these two, one needs to change the sign of the square root of 7. And algebraically, if we're just working algebraically, that doesn't actually change anything, but working over the reals, it's enough of a change that the groups you get by changing the parahoric at 3 plus are not actually, are not actually isomorphic to the ones that you get by looking at 3 minus. This is a little mysterious. I don't quite remember this, but so I won't try to tell you about it, but I do notice that contrary to what I just said, we seem to be using 3 plus, but also 3 minus. I do remember the answers to this, that if you look at all of these invariants, fundamental group abelianizations and whatnot, first homology, things like this, that the cases with 3 plus came out exactly the same as the cases with 3 minus. So these are things that will be difficult to distinguish, but they're not actually automorphic. Okay, I've finished.